Howdy. Everybody here? So this is the last talk of the day here in one of 3 or 4 rooms. So why don't we move on down here a little bit? Let's make this place a little more cozy. Come on, come on. Come closer. That way I'll be able to hear you when you start asking questions. I'll be able to hear you when you heckle me if that comes to pass. So come on down. Let's get closer here. Makes this a much more fun talk if you guys actually exist, as opposed to there's something out in the ether. This is much better. Thank you. That's much better. I mean, the thing that makes these talks fun is you guys, and so it would be a pity not to have that. So this is the first talk in 3 or 4 years now that I've given that I forgot my hat. It's like, oh man, I don't have the red hat on. So I'm going to wear the sunglasses for the first part, just so you don't recognize me. You won't realize that it was me that forgot those hats. So what I want to talk about today is kind of a controversial thing. It's about which algorithms really matter. And the place that the controversy happened, this isn't going to happen. Yeah, cool. No, not going to be me. But anyway, where this idea comes from is my background as an academic, where you want to drill down on ideas to the nth degree. You really want to figure out what the truth is, figure out really what the best algorithms are, figure out what the limits are for them. And for the last several years, I've been instead working not in academics, working with academics occasionally, but primarily what I've been doing has been industrial. And so this gives me this complete schizophrenic viewpoint of the academic and the industrial view, which are really, really contradictory. And so I want to talk about that a little bit today. And so feedback from the audience is going to be a big deal. So let's get going on that. So me, I'm Ted Dunning. You may not have known that. Claim to fame is I bought the beer at the first Hadoop users group. That was a long time ago. The key statistic to that was it was 4 hours long, 35 people, all the beer and all the food they could eat. And it was only $140 in downtown Palo Alto, which says these guys were too busy talking. They were so excited that was the first real hint that I had that Hadoop was going to go somewhere. If you could get that many people in a bar for that long and they forgot to eat or drink any of the food or beer. So that's what I did. And since then, one of the outgrowths of that has been MapR, the company I work for. We distribute a version of Hadoop that has some very interesting capabilities. We're not going to talk specifically about that, but that's for reference. That's where I come from. That's what I do. So let's just jump in here. What we're going to talk about today is what does important mean? You know, what's important differs for different people. I want to talk about why we say these things are important. And I want to talk about the difference between academic research and practical industrial developments, deployments, things like that. And I'll give examples, real examples that are in production today. So to me, what's important in an industrial, non-academic sense is first that code be deployable. Go ahead. And by that I mean that clever prototypes of the sort that I tend to build myself don't count. If they can't be standardized, if I can't leave them behind, it isn't real. If it's going to take the person who wrote the code to care and feed for it forever, that's just, well, to put not a fine word on it, that's bullshit to me. That isn't real. That doesn't mean it's going to work. And one of the things here we have is a 90-degree shift between mentalities. You have an inventor mentality, the person who's really novelty-driven, who has a to-do list of which they'll do 10% each day. And they think it's really exciting to have a to-do list because they have all these options of things to do. The other personality, which is 90 degrees, it's not 180 degrees, it's 90 degrees. There's no connection, no comprehension, is the administrator point of view. And there they have a to-do list, they're excited about that, and they want to tick off every item every day. Now, it's not a smart or stupid thing. Some of the smartest people I know are this administrator style. Some very smart people are this inventor style. Both are critical. But if you put the inventor in the administrator role, you will have a disaster. I have proven this myself by being a disaster. trying to be an administrator. It just doesn't work. And if you try to put an administrator in an inventor role, you'll have a slow motion disaster. Everything will work exactly the way it does today, which is exactly what you don't want to do in an inventor sort of situation, because you want those people to set the world on fire. You want to cause an explosion of problem. Second thing that these things need to do is be robust, which means that, no, that's fine. If there's mishandling or something like that, somebody doesn't just do exactly the right undocumented thing to the software's got to continue to run. It's got to continue to run when the inputs are a bit malformed. These are characteristics that are essentially never found in prototypes or academic research. And it also, at the same time, has to be very transparent. If there is a malfunction going on, the software has to tell you that it's not happy. Again, first prototypes almost never do that. Mature software does. And some kinds of algorithms allow you to find that out. Some kinds are just opaque. And we also need to match mindset, skills, and things like that relative to who's going to be running it and who's going to invent it. And in any company less than the size of the Manhattan Project, you have to decide what gives you the biggest bang per minute of effort. You have to apply the efforts where you're going to get response. So these are the things that I find important. Now, academic goals are fairly different than pragmatic goals. Reproducibility by others is key in academics, whereas it's exactly the other case in industry. I'd really rather my competitors could not replicate my results. And you want to be able to isolate theoretically important things in academics. But in industrial settings, you want to use synergies. You want things to work together. 2 + 2 = 17, not even 5. But in academics, you want to isolate those so you can study a particular thing. So we're talking just complete opposites here. And there's a strong novelty drive in academics. Academics only get brownie points for doing something new, whereas I only get brownie points for things that happen again and again and again, because that's called business. Anything else is called a hobby, at least by my CEO. So with pragmatics, we want to have the highest net value. Forget the moral sort of things. Let's just make sure this thing really works and really produces. We want to use available data, which means it's going to always be changing. Somebody else has control of pieces. Diligence and consistency, not necessarily my strength, but the strengths that I want to foster in my team have much higher impact than one moment of cleverness. The real cleverness is actually to make so a really good, diligent team can succeed in new ways. And so these are the things that I find that are contrast between the academic and industrial side of things. So here's some examples. First one is a way of making recommendations better. This is subject to the book that Ellen and I wrote a couple months ago, about a very, very clean way to deliver recommendation systems. And it's a nearly state-of-the-art result that you get. So let's walk through that. So, quick quiz. If anybody here has been looking at academic research, I don't know, it's not a terribly academic audience, but I imagine there's somebody here. What's the most important advance in recommendations in the last 10 years? Would it be co-occurrence analysis, matrix factorization, latent factor sort of things, or temporal dynamics where people change their opinions? To my mind, the result is random numbers, result dithering. We actually add random noise to results. That has been the biggest boost that I've been able to get small companies to have. I'll explain that in a little bit. And then simple business logic like anti-flooding. Just don't show them the same thing over and over again. Show them a few of those, a few of something else. Because if you're wrong on one, you're going to be wrong on all of them. And this is, again, an assumption that the academic researchers make, that every recommendation you make is independent. It's not in a real situation. Let's talk about the dithering. The real issues in recommendations are the fact that the recommendation engine shows you something, And then your actions inform the recommendation engine whether or not that was a good recommendation. And based on what you did, I might recommend something to you. But if I never showed you something, this particular item in question, I will never learn about it, and I may never learn to show it to him. These systems feed themselves. Their output one day is their input the next. And so if they don't explore, if they only go down the little narrow track that they know, they will never learn. They will only continue to do what they do. And so this exploration and diversity is one of the key things that you have to add to these systems in order to get them to work reasonably at all. And it isn't a matter of how they work against the training data on day one. It's how they work on the training data that comes in on day 100, which is a result of 100 generations of them producing alternatives, evaluating them, producing them, and so on. And that's a situation that is essentially never explored in an academic setting because it is completely uncontrollable. It is an artifact of all of the users interacting with all of the systems and all of those recommendations. That's just not a thing you can draw a circle around and study easily. The last fraction of percent, and if you think about it, how much difference does the very best from nearly the worst, or just at least the first sort of system you would do, how much difference does it make to go to the last iota of algorithmic quality? If you look at the Netflix challenge, the total improvement there was about 10%, of which 3 or 4% were achieved on the first few days. So we're talking about 6 or 7% over a year by concerted effort by the best people in the world. I would say that's a good measure of how much difference the best people in the world can make. They're going to improve your system 6, 10%. Maybe you've got better guys than the best in the world, maybe 11%. On the other hand, better exploration can make 100% difference like that within a few days. Because it isn't a matter of how good the system is on the data you give it, it's also how good is it at finding data to train on. And any system will do much, much, much better if you give it better training data. But only a system that is designed both to acquire the data and to learn from it will do both jobs. So this is a very interesting difference. So dithering is the solution here. Dithering is a way of reordering recommendation results so the top results stay near the top. It is done using random numbers, or at least pseudo-random numbers, and it's guaranteed to make your offline evaluation worse on the first day that you turn it on, because it's now exploring. It's now saying, well, I know this is the best, but I'm going to look number 17. Maybe that'll be good today. And so it's going to make it worse today in order to get that broader exploration, but it has almost a perfect record in my experience of about a dozen companies that I've advised on this, of making things better very soon. So this is the quote that I hear over and over and over again from people. They say, this made more difference than any other single change you recommended. So the way we do it is really simple. I mean, it's got Greek letters in it. Give me a break. That doesn't mean it's not simple. The idea here is that the rank, R, the rank that came out of the system, that's 1 through whatever, we take the log of that. Now, the property of the log is that big things have bigger logs, but they get bigger more and more slowly as they get big. So it goes up quickly, and then it gets up slower and slower. And then we're going to add noise to that. And when the log of the rank is going up slower, the noise makes a big difference to what order they wind up in after we add the noise. But at the beginning, when it's going up quite rapidly, it doesn't make a very big difference. This is just a hack to make that property happen, that things were highly ranked would still be roughly highly ranked, but things that were way deep might get dredged up to medium deep. So that's what we're going to do. And here's an example on this next slide. These were numbers 1 through 300 on each row. And what happened then is we reordered them using dithering for epsilon equals 0.5. And you can see that the number one item is in the top the one or two place in every case. So nowhere did it get pushed out of the top one or two places. It is the top item. But you can see that we get item number 24. What else do we get? Yeah, 24 is the deepest, but you see things in the teens appearing in the top 8 quite regularly. Next page, I think we have some larger noise. And now you can see that the top item is sometimes pushed down to the top 3. The top item, top spot, is sometimes taken by something as high as 11. We now have number 33. 33 appears twice in there. There's a 44 in there, I think, somewhere. But you can see that we're dredging very deep results up into these results. And so if we move on, the human behavior of this is that people, if we look at how quickly they click through or how readily they click through the top of the page because they start reading at the top, and they click through less and less as it goes down, and then very, very few people will go to the second page. So we get a click-through graph like this. It comes down. Yeah, that was dithering. Sometimes we show the next slide. Sometimes we show 5 deep. Yeah, that was exactly dithering. So anyway, we learn nothing as a result of people not clicking to the second page. We don't learn about what was on the second page. But people have this paradoxical behavior that if the second page sits there and it's stable for a few minutes, but they know it's going to change, that first page, they'll come back to the first page to see what's new. Ironically, they won't go to the second page. It's just a quirk of UI. And so this actually is a better way to get them to give you deeper information about this. So this is, if we back up one, you can look again. This idea of dithering, of bringing these deep results into the list, like each row of this, is a key advance in recommendations. And it's a completely pragmatic sort of algorithm. And you can imagine if somebody tried to publish a PhD on this topic. I added random noise to the results. It's not going to get you a PhD. It just isn't going to get you anywhere in academics, but it will make your recommendation engine much, much better. Next. So here's another. So this is the lesson. Exploration is good. Exploitation in a business setting is also good, but exploration is how you make exploitation better tomorrow. That's the lesson. Now, here's another example. This is a bit more advanced. This is something called Bayesian bandits. Here, we're going to codify the system. So instead of just adding random noise because we know it doesn't know the answer, so instead of just injecting it by hand and by force, what we can do here is we can let the system learn not only what it knows, but also to encode what it doesn't know. If the system encodes in every parameter not only knowledge but ignorance, then we can use that degree of ignorance to do very, very principled dithering. So the basic idea here is based on something from a guy named Thompson who came up with this in 1935. And it's a very, very general way of building sequential statistical tests. The idea was essentially forgotten in the 30s because the world wasn't ready for Bayesian sort of things back then. My man Fisher, the eminent mathematician, I say, she calls him a biologist. She's a biologist, I'm a mathematician. You can see the, it takes one to know one sort of thing. He was just very much not a Bayesian and really distrusted those sorts of things. If it didn't have physical existence, he didn't want to talk about estimating it. But this Thompson sampling is a very, very nice way to do this. And what it does is if we're going to do any particular test, say if I've got a coin, if I've got 2 coins, and I'm going to flip the coins, and I'm going to try to decide which one is more likely to come up heads, then I have to try them both. And I'm going to explore, and so on. And if one of them is worse than the other, then I will have a regret for having tried the one that is worse. That's just the way that things are going to go. And the degree to which I have to experience regret in order to learn is this mathematical regret. And Thompson sampling has provably very close to optimum regret. I mean, I only regret that I didn't actually have a coin, but that's just the way it goes. This is the best known solution, and it's incredibly simple. Let's walk into how it actually works. Well, this is kind of how it works. The basic idea is we're going to do some really fancy integral inside this, but we're going to do it purely by sampling random numbers. Let's go to the simple part of the answer. We're going to sample parameters. So these parameters are whatever we use to describe the system. Might be the probability of heads, might be probability of conversion on an ad, might be the degree that the blue picture causes to encourage somebody to click. Might be any of those sorts of parameters. And we're going to sample it, not estimate it. We're going to sample it from the whole range that it might have. Back girl. We're going to sample it instead of estimate it. And by sampling it, we may get a low value, may get a high value, whatever within the range of ignorance. And then we'll pick whichever alternative of the things we can do right now that appears to have the highest reward given the sample we just took. It's really simple. I mean, it's actually easier than estimating these things in many cases. We're going to sample a value, and we're going to see which one's biggest. It's dead simple. And we're going to record the result of using that result. And we'll learn from that. That will decrease our ignorance, improve our knowledge. That's the algorithm. It's that simple. Now we can do this. And here are some concrete results. This is against one of the better known A/B testing algorithms called epsilon greedy. That's in red, whereas the Bayesian banded is in gray. And the vertical axis is regret, instantaneous regret, and the horizontal axis is number of trials. And you can see right away that this thing is considerably better. If we go to the next slide, we see another graph. Now this is total regret, so it can only go up, which my mother told me that a long time ago, but it's obviously true mathematically here. And what we get are these different graphs for different algorithms, and the total regret there for the lower line, the blue one, you can tell it's blue, is for Thompson sampling. The second best one is for what's called linear upper confidence bound algorithm, which is, was not an algorithm developed at Berkeley, even though it has the initials UCB on it. It is very good as well, but it's much more complex, and it is not applicable for systems that are one step removed, where the parameters change how the people will react to context rather than directly being applied. So it's a very difficult thing to apply. And then exploit is just pure exploitation, and then epsilon greedy, which not long ago was the state of the art, is a whole lot worse. So this is a very, very cool algorithm, and it's incredibly simple. Many, many systems aren't plausible to postulate in this fully Bayesian form. The ad predictor work out of Microsoft, or the TrueSkill system, also same group there at Microsoft, has shown, though, that even though you can't really provide the mathematical form that you want, you can come pretty close with very simple message passing type learning. And you can't apply Thompson sampling without that posterior sampling capability, but that often is not that hard to come by. And you can build that into a production system. And if you can't do that, you can always just add the random numbers, approach number one. These are very, very practical things. If you can use Thompson sampling, do it. If you can't, use dithering. So that's lesson 2. Exploration, really principled exploration, is pretty easy to do and pays big benefits. Now, here's another pragmatic thing. Clustering. Clustering is actually a very, very useful thing. I gave a talk yesterday about anomaly detection. The cornerstone of that was clustering. We cluster these signals. A cornerstone of a lot of image processing is different forms of clustering, either sparse coding or honest-to-God clustering. And so it isn't usually used the way most people think of it, is to divide things into groups. It's usually used to come up with a sparse feature for a machine learning system, or for some quantization of something down to an acceptable level. So when you see a video camera, no, not a video camera, digital camera, it does JPEG encoding, and that depends on clustering. If you see on the web there are 216 colors that are commonly used, those were determined by clustering. Those match up to your perceptual capabilities of colors. And so clustering is a pretty cool thing. Let's look at how that works. And k-means clustering, which is used with a normal distance, is very useful compression and extraction. It was originally invented for signal compression. But it can be very difficult to apply in high dimensions and for very large amounts of data. So anything more than linear scaling just doesn't work. Now, it is possible, however, to do clustering in one pass through the data with high quality. This is a fairly recent result. The way we do that is by making a sketch, a representation of the data, which if we cluster the sketch, we will get a clustering of the original data. Here, for instance, is data. And we could represent this by clusters. And if you look at it, we could use a lot of clusters to represent that. More clusters perhaps than we think the data really needs, but by using lots and lots of clusters, we can get convergence guarantees that we wouldn't get otherwise. So the idea then is that we can compress this data by using clustering. And next, Ellen. This is how the data looks after clustering and after diagonalization. And here's another example where we looks like we have 4 clusters, at least visually, but we could just spatter lots and lots of clusters in there. It's a good representation of the probability density. And if we only had the triangles instead of all the colored points, you could still imagine, especially if the triangles were weighted according to how many data points were close to them, you could imagine you could still figure out how the data should be clustered. This is the idea of sketching. And here is the failure we want to avoid. This is a failure of normal clustering algorithms and why they are typically multipass and why they are expensive. What happens is if we have initial conditions, so we put 2 cluster centroids into one actual cluster, it'll split that cluster and never recover. But if we were, instead of trying to use 5 clusters here, if we were using 30, the chances that we would not put at least one center point in every one of those actual clusters are nil. And we could pass through all of our data like that. And we'd get 30 sketch points, and we could cluster those and get a high quality clustering. That's the idea. That's easy, that's quick, that's incredibly fast, because it doesn't even have to do an exact search for the nearest cluster as it's making the one pass. So it can be log of k sort of speed as we go through there. This is fast. This is amazing. And this is a pragmatic, practical idea. It had a short life as an academic algorithm. And what do you do next? Well, you don't do this next. You have to do something new. So lesson 3, sketches in this style make big data small, and you can apply difficult algorithms to that small sketch. That's a pragmatic thing. Search abuse, that's one of the big ones. That was the subject of our first little book, was how to make a good search engine, a good recommendation engine out of a good search engine. Here, let's go. You can imagine this is the standard sort of discussion of recommendations where everybody comes in with some things they bought in the past, and Bob happens to have bought an apple. Alice previously bought an apple and a puppy. So let's recommend for Bob a puppy, right? Makes sense. Makes real kind of sense, especially to Bob because he likes puppies. Now, this is using what's called co-occurrence, the co-occurrence of apple and puppy. This is a co-occurrence matrix. This is what we formed to do this. And you can, or this is a history matrix, sorry. You can see Alice has had a puppy and an apple, and now she's had a pony because everybody wants a pony, of course. And what we want to do is look in this matrix at co-occurrence. But you notice that pony co-occurs with everything. So we want to find apple and puppy because they co-occurred interestingly, but reject pony co-occurring with anything because it's boring because it co-occurs with everything. So we do a test to reduce that to just a few co-occurrences. These are called indicators. And we do that by doing a 2x2 analysis of just when things occur together and when they don't. I'm skipping through this quickly. We can find it other places that the actual full details. That leaves us what's called the indicator matrix. and we add each row of the indicator matrix to an actual search document. Click. That last field there, the indicators field, is not normal text. The rest of it is normal text. That's the stuff you would have. The indicators there are behavior. We're indexing behavior. We're indexing significant indicator behavior. If you have an apple, that's an indicator we should retrieve puppy. So we can use your behavior of apple consumption to retrieve things that apple consumers should see, in this case, puppy. Let's move along. Here's a picture. Next. Here's a picture of a retrieval interface, and here's a particular retrieval from that where we've used a query which is indicator artist. This is for music of 2122, this is Fats Domino, or the Beatles. And we get Chuck Berry. I don't know if that's readable for you, but it's probably not. Might be. But the fact is that last field there is indicator artists. These are behavioral indexing going on this. And that behavioral indexing allows us to do behavioral querying. So at the cost of one co-occurrence analysis, we can inject these indicators into a search engine, and you've got a recommender. In fact, you've got a composite text and behavioral search engine that can be used for recommendation or text retrieval or combinations of those. You can put geolocations on there. You can restrict all your search any way you like. This is a huge thing. And again, not very academically applied. Here's an example. This is a real example going against videos. We have two kinds of behavior, people typing query words and people watching videos. And the real query here is Paco de Lucia. He was a guitarist who died just a few months ago, and he was known for Nu Flamenco. And if you look at the results here, what you get are Hombres de Paco, which as far as text is concerned is a great hit, because there's 2 out of 3 words that match. I mean, you never get that, right? 2 out of 3, de and Paco. Unfortunately, it's also known as garbage. That's the technical term here. It's just completely not relevant. Here are the recommendation results, however, where we're recommending for people who ask for Paco and de and Lucia, here are the videos that we should show. There are no Paco de Lucia videos in this corpus. There is no way to be correct. There is nothing labeled with his stuff. But the top hit here, if you look at it, is somebody playing classical guitar, the Concierto Ciudad de las Partes, the first part of that. But if you notice, they're playing it on a jazz guitar. This says Paco de Lucia all over it. It wasn't him, but it's somebody playing jazz guitar with a classic Spanish classical standard. The second one is interesting. This is a group called COD. They're dancing a dance called the bulería. Bulería is a kind of flamenco dance, which of course is accompanied by flamenco, which is of course related to Nu Flamenco, which is of course what Paco de Lucia did. It looks like somebody encoded a very careful ontology of all of this content. And in fact, somebody did. Those were the users who watched these videos. They did it for themselves to make themselves happy, but they did encode this knowledge by behaving the way they want to behave. And what is meaning? Meaning is the way we explain behavior. If this thing explains behavior, it has meaning in it. The third one is an actual classical guitar performance. The fourth one is Van Halen doing a classical guitar riff during a concert. And then the last one is a guy doing freestyle flamenco in his dorm room. He's imitating Paco de Lucia. Kick ass. And takes a few hours to implement. You can literally do it over a weekend. So here's a pragmatic algorithm that matters. Lesson 4, recursive search abuse works recursively. It works and pays off really quickly. Search can implement recommendations. Recommendations can then implement search. Instead of the things that actually have the words that you're searching for, we can give you the documents that you should have been asking for. That's a cool thing. Let's go. So the summary is, there's a lot of pragmatic algorithms in there. They aren't the ones that are sexy necessarily, but dang, they are the ones that are cool. They really, really are things that can pay off quickly, easily, and can make your life better as data handling people. Are there any questions? Yeah. Wow, that was quick. Do we have a microphone for this fella? No, you can't. Not even I can do that. This is a big room. That's why I had everybody pull down so we could hear better.
Can you recommend, with K-mean is always you have to know the cluster ahead of time. Can you recommend something that can process massive data without knowing the cluster ahead of time? The number of clusters ahead of time.
So K-means can be
dbScan or something.
Yeah, K-means can be adapted into alternative algorithms which do not know the number of clusters ahead of time. And in fact, you can do it in a variation so that it doesn't even know the number of clusters afterwards. Now that sounds bad, but what I mean by that is that it can actually do a non-deterministic clustering so that at the end of the clustering, it has multiple solutions for you. So if you had asked for 2 clusters, I would have given you this. If you'd asked for 200, I would have given you this. And it can give all of those to you in one pass. Yeah, actually, variants of that one will do that. Will do exactly that. Now, there's a bound on K that you have to set at the beginning of that sketch. You have to have a complex enough sketch to discover clusters at the biggest value of K that you have. But you don't have to set it to exactly the right value. So you just say, well, I don't want more than 100 clusters. I think I want around 10 or 20. So I'll set it to 200. And it'll produce a sketch that's bigger than I would have gotten otherwise. But now I can analyze that sketch and I can produce non-deterministic clusterings. I can do all kinds of things. There's also an algorithm called dpmeans, which is a non-deterministic version of that. And you don't know how many clusters it will come out with, but you do know the size scale that you start with. And that's a variant of the fast pass there. The variants of them are single pass. You can do single pass algorithms, yes. He really likes to ask questions.
I think you mentioned that this was implemented in Mahout. Sorry.
Yes, it is implemented in
Mahout, correct?
Yeah,
if
yeah.
I remember.
And I think that shortly there'll even be much better versions in Mahout that run even faster.
Right. Thanks.
Yeah. That doesn't mean nobody else can implement it. And if you're curious about this, if you have your own machine learning library, you want to try it out, give me a holler and I'll help you do it. This is open source after all. We share. It isn't trying to lock it down. Any other questions? Surely there were. I thought there was somebody wiggling. Maybe they were just wiggling. I'd like to say that this is like an auction. She has a comment.
Yes, that the ebook. The first book he referred to in the Practical Machine Learning series is available as an ebook still for download. If you go to the MapR website and search for Practical Machine Learning Innovations in Recommendation, you can get that, and part of what he talked about is covered in that book.
And the anomaly detection one is available there, and later ones will be available there as well. So yeah, and there's a Kindle version of that available on Amazon as well for free. I think it's probably the only thing that's free on Amazon, except shipping. Any other questions? Well, we may have to break for coffee and things like that if you guys don't want to ask public questions. We can all ask private questions if you like. I'll be around for another 20, 30 minutes if anybody wants to talk about this or any other related topic. And thanks for coming. This has been quite a show, hasn't it been? Thanks to you.